other than doing 1,2 hydride shifts, we can also do something else, or the molecule can do something else, and this is referred to as ring expansions. So ring expansions are going to take advantage of the fact that once we make this charged intermediate, we can do kind of this architectural shifting for the molecule. So once you actually make the molecule charged, you can think of it as kind of a Rubik's Cube that you can kind of twist and turn. Let's go ahead and I'm going to add HBr, and at this point, the first two arrows that you're going to do to perform the mechanism, it should be pretty trivial at this point. So let's go ahead and draw the result of that particular arrow push. So now if we had to choose between carbon 1 and carbon 2 to put our positive charge, at this point it should be a very obvious choice that we're going to put our positive on carbon 2 to begin this process. So if we had to categorize, we could call this guy secondary carbocation, so secondary carbocation. So let's talk about two potential shifts that you could do. The interesting thing about these shifts are that hydrogens are not the only things that can move. You could also potentially move carbons. So this methyl group right here. So if we did this 1,2 methyl shift, we'd utilize this methyl right here, and we could move it over by 1, just like we did a hydrogen. And if we did that, we would get a new form of the molecule. So we'd have a 4-membered ring, and we could get this guy moving over here, and 1 carbon here, and we get this carbocation moving over by 1 position. So this is actually a pretty good move at this point. So we go from a secondary to a tertiary carbocation. So overall, this is a pretty good move. And that's probably where we would end if we didn't have a ring. So a couple lessons here, I guess. Keep in mind the fact that you can do 1,2 hydride shifts, but not only can you move hydrogens, you could also move methyls. So we could potentially move this methyl right here to this position right here to stabilize that carbocation. Because we have a ring, we can also take advantage of another stabilizing effect, which is called this ring expansion. We're going to try to number this molecule a little bit more. So let me go ahead and put numbers on everything. So it's gonna be obvious in a moment why we numbered, because if we didn't number, it's gonna be very easy to lose track of where carbons are and make little silly mistakes. So if it's possible to move this 7th blue methyl, it's also possible to move this 6th CH2 group. And so just like we move the methyl over by taking the electrons between 7 and 3, breaking that bond and moving methyl over 1, we're going to be able to do the same potential thing between 3 and 6. So a really important point to make sure that you can try to follow along with is that since it was valid for us to move 3 to 7, if we could break that bond, we can also potentially break the 3 to 6. So that's what I'm going to do. I'm going to break that 3 to 6 bond and move the electrons over to that 2 position. Okay, so just like we were able to move that blue methyl, we are also able to move this kind of purple 6. And what I'm going to do is I'm going to redraw the molecule, and this is probably one of the hardest things to visualize at the very beginning. The bond that we broke was the 3 to 6 bond, and so what we retained was the 2 to 3 bond. So that bond is not broken. The 3 to 4 is still there because we didn't break it. 4 to 5 is still there. 5 to 6 is still there. And so then the thing that we have to remember or think about is, what bond are we making? So we broke that 3 to 6, it's no longer there. So the bond that we're actually making is between this purple 6 and the 2. That means that once we redraw the molecule, we're going to have 1, 2, 3, 4, 5 carbons that are going to be in a ring. So we know we're going to have 1, 2, 3, 4, 5 carbons in that ring. We might as well just go ahead and draw a 5-membered ring. And again, I have no idea what carbon is what at this point, so I'm just going to start numbering very arbitrarily. So I know 2 is going to be part of the ring, and I know 3 is going to be part of the ring, so let me just start numbering like that. So that's carbon 2, 3. We know 3 is still attached to 4, so that must be 4. 4 is still attached to 5, that must still be 5. And 5 is attached to 6, that has to be 6. So I'll go ahead and put a purple by 6. So now we have to keep in mind the things that we're missing. So we're missing, at this point, the blue methyl and number 1. So where should the blue methyl be? The blue methyl should be attached to carbon 3, so that's carbon 3, so we know that we have to have that blue methyl attached. So I'm just going to draw that methyl group. And so the thing that we're missing now is carbon 1. So carbon 1 used to be attached to 2, and so since we didn't show that bond breaking, it still must be there. And so now, just to make it a little bit more explicit, what I'm going to do is talk about these electrons that used to be between 3 and 6. So these bonds, or these electrons between 3 and 6, these used to be them. So these used to be the blue or the green electrons. And so now these green electrons are now going to exist between 6 and 2. So I'm going to redraw that bond, color it in, and that's our green bond. These are the electrons that used to be between 3 and 6, and now they're between 6 and 2. Okay, so now the thing that we have to keep in mind is, well, we have to keep in mind the charge conservation. So if the charge used to be overall net positive on the left, the thing that we're missing is the charge is not net positive on the right. So the question then becomes, well, okay, how many or which carbon actually gets the charge? And just to kind of zone in on the area of interest where we can potentially have that positive, we're really going to look at the 2 atoms that used to have a bond. And so really what's going to happen is we're either going to have that positive charge either on carbon 3 or on carbon 6, because the bond that we broke was that green bond, and 3 and 6 were the atoms that were making up that covalent bond. So what I'm going to do is kind of inspect carbon 6, and I'm going to inspect carbon 3. So if you look at carbon 6, the purple, at the very beginning this guy's neutral. So that means that he must have 2 hydrogens attached to him. So 2 hydrogens attached to him to make him neutral. And so if we go one over to the right, we'll see that 6, we haven't really shown either one of those carbon to hydrogen bonds being broken. So they must still be there, and if they're still there, well, that means 6 is neutral. So that guy checks out. And then if we think of this carbon 3 actually used to have 0 hydrogens on him. And so if we think about this carbon 3, if you have 0 hydrogens on him to begin with, and at the end of the day you have 0 hydrogens, and we do a formal charge calculation, it's going to be 4 minus 1, 2, 3. That means the positive charge is going to be on carbon 3. And just to kind of keep things kind of wrapped up in a nice neat little bow, let me go ahead and circle these guys. These were the atoms that we were thinking about to begin with, and I just want to prove to you that carbon 2 is no longer positive. So initially that carbon 2 had a positive charge, and it had a positive charge, which means that it had a hydrogen attached to it. So we didn't show that hydrogen to carbon bond breaking, so it still must be there. And so that must mean this carbon 2 has 1, 2, 3, 4 bonds to it, so it has to be neutral. Okay, so that was a lot, but at the end of the day we found out that carbon 3 got the positive charge. And now that we've done all that legwork, which was actually kind of, a little bit difficult, but after you do like 5 or 6 of these, it gets pretty easy. But after you do the hard part, the final finishing move is pretty simple, which is the bromine just attacks that carbon. And at that point, you can just redraw the molecule. If you compare and contrast this molecule up above, which it makes a tertiary carbocation, you ask yourself why we even went to this this effort and this headache to do this ring expansion in the first place. Well, if you consider the molecule right here, it turns out that this is also a tertiary carbocation. So really this is an apples to apples comparison. They're about the same amount of stability. But what acts as a tiebreaker here is the fact that as you change the size of these rings, as you go from rings that are very tiny to rings that are very large, the stability increases. So stability increases as you increase the size of the ring. So this is also a very good driving effect as to why we get this ring expansion and why this molecule on the right is going to be our major product. So I guess one thing to take away from this is if you're doing these kind of problems, always try to look for the ability to do a ring expansion. And if you can do one, go ahead and try to go down that alley. So ring expansions are going to be really stabilizing. It probably will take at least 3 to 5 problems of doing this to really kind of get the hang of it, and it's really overwhelming at first, but after you do a handful of problems, they should become almost second nature. So even if it seemed kind of weird, don't despair, they'll get easier, I promise.